Welcome one and all to my tutorial on unsupervised deep learning for beginning. I titled this a hands-on tutorial because I want you to actually mess with a little bit of code so that you can get acquainted and lose that first step fear into diving into deep learning. My name is Pablo Rivas and I'm assistant professor of computer science at Baylor University. This presentation, this tutorial has also a TA, Korn, and he's going to be helping me answering some questions on the chat. If you want to ask some questions, and I'll be able to answer some of them as well as we pause for a moment. My contact information is here, and feel free to send me an email or also call the office. I want you to know about these resources that I have put together for this particular tutorial. So up on the top left, there's a website called rivas.ai/tapia20. I realize that there are many people that might be interested in this and may have certain disabilities. So this website has the slides. If you want to go fast, slow, you can do that as well. And this website also contains the actual code that we're going to be showing on the screen. And I would like you to go there right now and have that website open, because you're gonna need to mess with this code and run the code by yourself. So you're gonna click on opening Colab. You're gonna need a Google account for this, by the way, because Google Colabs belong to Google right now. So you will need a Google account to access this. So once you open these codes, these collabs, you will have access to the 3 modules that we'll have. The first module is Autoencoders, the second is Deep Autoencoders, and the third one is on Variational Autoencoders. So as we go, we're going to be opening these collabs, and I want you to mess with these inputs or with these models a little bit as we go. So please have this resource open. In the first module, Autoencoders, what I want you to be able to do is to know the difference between unsupervised and supervised learning. I want you also to know how to implement the 2 basic layers of an autoencoder. I want you to be able to apply an autoencoder to a dimensionality reduction problem and also data visualization. I want you to be able to evaluate and know the risks associated with unsupervised learning. In 2018, I was in a conference where a presenter, A. Graves, proposed this division of learning, these categories of learning, if you will, in which in columns we have label data and no labels. And on the rows, we have active and passive. And so, for example, supervised learning is considered something that is very passive, but has labels in it. And passive in the sense that it happens only once and usually are done with it, while reinforcement learning or active learning requires certain iterations over and over and over again, and the satisfaction is not clear, the degree of satisfaction that you use. And in the case of not having labels, for example, unsupervised learning is in this area of passive learning. And unsupervised learning, just so you know, in a recent conference in New York City and AAAI, I remember vividly that one of the ACM Turing Award winners, John LeCon, was there, and it was saying that perhaps unsupervised is a misleading word, in the sense that people may think that there's no supervision involved in this type of learning, while in fact, unsupervised learning has a lot more supervision, usually a lot more supervision than supervised learning. Think of this, for example. If you have a picture of a number or a cat or a dog, and you're trying to differentiate whether it's a cat or a dog, you only have two supervisory signals. It only says if it's a cat or a dog. That's it. Two supervisory signals. While in unsupervised learning, and usually, for example, in an autoencoder, the one we're going to talk about in a moment, that autoencoder is meant to replicate whatever input it is. So let's say that the picture of a dog or a cat is 100 by 100 pixels. So at the end of this autoencoder, you'll also need to reproduce exactly that image of 100 by 100 pixels. So those are the supervisory signal. So compare 2 to 100 by 100. So in this sense, the community is proposing renaming this to self-supervised learning. It's a better terminology for unsupervised learning. And there are even t-shirts, I think, out there that says the future is self-supervised. So I just wanted to make the distinction that if you ever hear or come across the word self-supervised learning, know that some people would actually understand the same thing as unsupervised learning. Let's talk about autoencoders in particular. If you consider a neural network in which every node is connected to another in a feed-forward fashion, an autoencoder is supposed to take input, an original vector like in the picture with 8 dimension, and somehow have this bottleneck type of architecture in which there is a reduced number of neurons, for example, in this case, in the fourth layer, 2 dimensions only, or 2 neurons. And the idea of the autoencoder then is to find this unique representation, we will call it a latent representation. And out of that information, or this latent representation, its sole purpose is to build back or reconstruct the original input. So the first part, we call it the encoding part. And the second part is the reconstructive part. We call that the decoding part. Usually, not always, in autoencoders, we are looking after getting this latent representation. That will be one of the main points of doing an autoencoder. If you're wondering when can we use this, well, the first and obvious part is using, you can use it in dimensionality reduction. So we can have highly dimensional data represented in, for example, in 2 dimensions. We can also use this to learn representations that are not biased against any preconceived notion. If you think of a classification system that is trying to determine whether a picture is of a cat or a dog, it will only learn features that help it, the model, be discriminatory against these 2 categories. While an autoencoder, for example, is not biased against learning anything in specific. But if you show him enough pictures of cats and dogs, he will learn that those have some things in common, and it can compress data, which is another use for autoencoders, data compression. Because of the dimensionality reduction, it can aid in clustering as well and performing really fast searches on the clustering space or in the dimensionally reduced space. And also we can do data processing or consider this a pre-processing module that will prepare your data for another stage. Let's say that you plug in after this a support vector machine. You can totally do that and consider the autoencoder as a pre-processing strategy. So I'm going to use this graphical depictions or representations for an autoencoder, and this funnel kind of thing, it's called an encoder, and that will represent all the layers necessary for an encoding until you get to the latent representation. And also I'm going to use the upside down funnel as a decoder. Okay, so without further ado, I'm going to show you how to code using TensorFlow and Keras these elements of an autoencoder. First of all, I'm hoping that you already had this website open, and hopefully you already opened your Colab with the first module on autoencoders. The first thing that I want you to do is be aware that this variable of input dimensions will likely change. They're gonna make you do something in a minute, and this is the first thing that you may need to change. In the code that I'm providing, be aware that if you use this code for something else, you should come back and edit the number of dimensions in the input toward your specific application. And so the encoder is composed of layers. We call these dense layers or fully connected layers. And here I'm saying that this has 6 neurons, 6 neural units, an activation function of type sigmoid, and takes as input the input vector, which I just previously declared that has a dimension of 8. This type of programming in Keras TensorFlow, it's called the functional paradigm. So we code the layers as functions that take arguments. The other approach is a sequential approach in which we add in a sequence layers on top of layers. Both work the same, but I'm going to use here the functional approach. Well, we continue adding more layers, another dense layer with 4 neurons, same activation function, but this one is taking as input the previous layer that I call E layer 1, the encoder layer 1. And then I defined a last dense layer that has neurons defined in latent dimension 2. And I specifically chose 2 because I want this model, I want to be able to plot this model in 2 dimensions. But if you chose a larger number of dimensions, which is completely fine, you may not be able to display them in 2 dimensions. So for this exercise, I wanted to see the powerful nature of an autoencoder visually in 2 dimensions. Okay, so this last layer, I called it the encoder. And finally, we declare a model, a machine learning model that takes as input the input vector, and also learns or looks at an output from encoder, which is the last layer. We call this model the latent encoder model. Then we can start looking at the decoding layers. The decoding layers then become this dense fully connected layers as well. And I'm working backwards. So if in the previous layer, I went from 8 to 6 to 4 to 2, now I'm going from 4 to 6 to 8 dimensions. Okay, this is the same activation functions for all of them, and this takes as input the encoder, the layer, previous layer, and layer 2. And this last one contains the output of the last dense layer that is supposed to have decoded the original input or reconstructed the original input. So we call this the model an autoencoder that takes input, the original input, and the decoder, which is going to output the reconstructed part. The model also needs a loss, and the loss is what fitness function it's going to use to run gradient descent on. And one of the most typical on autoencoders is the mean squared error. It's typically defined as the average difference of the average of the score differences added together. So the mean squared error is the loss we're going to use, and we're going to use an optimizer called SGD, stochastic gradient descent. And with this, we would have compiled our model. Of course, we need to do a little more with it, which is train it. And for this example, I just want, as I said, I just want to train it with 8 inputs. Very simple. I'm going to take a vector, a binary vector with zeros and ones, 8 of them. So it's actually 8. And then I'm going to call fit on my autoencoder, passing as training data X and testing data also X. Usually the second argument in fit is the testing data, but because we're trying to reconstruct the exact same thing as input, the actual target is also X. So this is the input and this is the target. So I wanted to learn to reconstruct this vector exactly using on 1,000 epochs. Okay, so once this line is executed, it will take a little bit, not a lot of time. Then we can call on the latent encoder, which is a model that will take X and convert it into 2 dimensions, into this latent space. And we can also call an autoencoder on and predict on X, which should hopefully give us X. So we're saving this X approximation unencoded, and X hat contains the predicted or the reconstruction. So if I print encoded, we will see something like this. Because of the nature of randomness in an autoencoder and unsupervisedness, these are likely to be different for you than for me. And so it will have 2 data points here. And this is the 2-dimensional representation of this 8-dimensional binary string. All right, and when I print X hat, which is the approximation, I get this second vector down here. And so, as you can see, the first one should be a 0. It is a 0.09. Okay, close enough. Second one also should be a 0. The third one should be a 1, and it's a 0.90. Close enough. The next 2 should be zeros, and it's a 0.08, 0.09. The next 3 should be 1s, and it's a 0.9, 0.9, 0.9. So as you can see, this is an approximation. It is not perfect, but it's close enough. And so we can also calculate the actual mean squared error by taking the input X and the prediction. We subtract it, we square it, and we take the average of that. And so the mean squared error for this particular training sample, it's 0.008. Okay, so hopefully this will get you started. But now let's do a little more interesting. We can see or observe what is going on during the training process, because when I did fit, I saved a history of the training process, and then I can plot what happened across the 10,000 epochs that I defined. So as you can see, the mean squared error was declining rapidly until it got to this point. All right. So far, we showed that this converges. But what if I take a different 8-dimensional binary vector and I pass it into the model to produce into a latent space and also to reconstruct it? Now, I am not retraining the model. I am simply using that data and plug it into this already trained model that was trained with only 1 vector, which is a terrible idea, but you'll see why. So if I predict or call predict on this vector, this is the number of the 2-dimensional representation. These are numbers. So it's 0.21 and 0.31. If I compare this with the previous one, you will see that is nearly identical. You see that? 0.2123. It's 0.2121.3. So if we look at the reconstruction as well, we're using this vector X, we get, when it should be a 1, we get a 0.09. When it should be a 1, we get a 0.09. In fact, I believe this is the exact opposite vector. 0, 0, 1, well, almost the exact opposite. Yeah, so actually it is the exact same opposite, right? Look at this. So it is predicting the other vector. This is called overfitting, and also poor taste in machine learning. So this is in purpose, so that you could see that we need a lot of data usually when it comes to unsupervised learning, so they can generalize and learn things better. So when you give it duplicate, it will tend to create some type of bias toward particular data points or samples. So the more diversity you have in the data set, the better would be your autoencoder. So once again, it's a lesson that diversity is good and bias is not so good. All right, so how do we fix this? We can fix it simply in producing and training it with a lot more data. As you can see, the mean squared error of this reconstruction is severely high, 0.82, compared to the previous one, 0.008. All right, so let's do something more interesting. Let's talk about this data Minced, that it's a collection of digits, 100 digits, introduced by Jan LeCun in 2010. And the whole point is that we have a ton of images of these numerals. And we would like to create perhaps here an autoencoder that can learn these shapes of the data. So we're gonna do this right now, and hopefully we can do this together and mess with the data a little bit. To load the training data, you can simply invoke this from Keras datasets, which is already loaded or into the functionality. And it will download the data into your computer. It will take a few seconds, and we need to do a couple of things to the data before we can use it. And this is only for normalization purposes, because images are 28 by 28 digits on grayscale, goes from 0 black to 255 white. We would like to have this data being floating in 32 bits, floating point 32 bits, and we would like to divide it by 255 so that the range of values is from 0 to 1. 0 being black and 1 being white. And also we'd like to reshape this so that instead of being 28 by 28 matrices, it's a single vector of 784 dimensions, like this. So just to show that the training set will have 60,000 images of numerals and the test set will have 10,000. I would like us to do experiments right now and look at how this data will be learned in different aspects. So I already did an experiment, but you can prove this to yourself. If we create autoencoders with only 2 layers, like this will be sort of the approximation that you could get from an input vector or the reconstructed vector from a 4, might look like this. If you use 4 layers, it can look like this. If you use 6 layers, could look like that, or even 8 layers could look like this. If you want, you can also experiment with the number of neurons here, but I highly recommend that you either go down in the size like a funnel, the number of neurons, and then reconstruct back up to the number of neurons, or at least that you maintain the same number of neurons. Of course, you're free to do as you wish, but this is a recommendation. In practice, this usually works nice. So we're going to do right now one of these architectures. We're going to perform the one with 8 layers, the one that has 392, 28, 10, and 2. If you wish, this is what I want you to do right now. Go ahead and type different number of neurons here, but don't go too high because it was going to take too long. So I encourage you to either try the same number of neurons here and there, or some different number. You go and be free of doing as you wish. Okay, so these layers, as you can see, the input dimension changed because now we're dealing with 28 by 28. So this is going to be a 784 input dimension vector. This has the same structure that we had before, and I'm arbitrarily defining this number of layers because I believe this is half of 784, which is the input dimension. And then 28, this is the next layer. So in a way, at this layer, I am compressing what was a 28 by 28 image into a vector of 28 by 28, or 28 by itself. And then finally, I do this with 10 and 2. All right, so let's just reflect on this for a second. We're asking this autoencoder to take 28 by 784 dimensions, 28 by 28, and represent a number, the picture of a number in only 2 dimensions using 2 values. All right, and the decoding is also going backwards using the same. We will create a model, an autoencoder, and we're going to compile it. And now we're going to use a different laws, a binary cross entropy. Because the original reconstruction that I was showing earlier was an arbitrary number, zeros and ones. I could have used the mean squared error, binary cross entropy, or another loss of your choice. Here I like binary cross entropy because we want to impose into the network learning a little more carefully the probability distribution of every pixel in this in the input layers, and also to reconstruct them as perfectly as possible. We're going to use a different different optimizer called Atom, or adaptive. It's an adaptive gradient descent method, very powerful and fast. And the one previously used, we used SGD, stochastic gradient descent, just to show you that there are other options. So we're going to train this for 100 epochs with a batch size of 256. We're going to shuffle data, and we're going to do validation data, X-test, so we can report and see the results on validation data. So after we train this for 100 epochs, this is going to show a curve like the following. Now remember, these curves are going to show differently for different type of losses. The binary cross entropy loss may have a different scale, of course, than the mean squared error. But the point of it is that both of them converge or meant to go down all the time. That's why they're called losses. And the binary cross entropy is given by the probabilities, or if you're familiar with the concept of entropy or cross entropy, this is where it comes from the definitions of probability. Okay, so after the model is trained, we can actually predict the entire test set. Remember, we trained with the training set. The test set was never seen during the training process by the model. It was only seen to make calculations of the error as we go, the error being this pink line. And we also have the predictions with the autoencoder, so we can get the reconstruction. So in this figure here, we have the reconstructions for the numbers 7, 2, 1, 0, 4. And as you can see, this part of the 4 looks like a little bit like a 9. This part of the 4 also looks like a 9. And this 9 actually, yeah, looks like a 9 a little bit. But the more interesting part, I think, that you can see is by looking at this vector. By the way, these are the x hats, the reconstructions, but the encoded, those two-dimensional representations of every single number can be displayed here. I'm going to rename it as x underscore using a 4-layer encoder. Remember, it was a 8-layer autoencoder, but the encoder part is on 4 layers. So if we plot this data and we assign a color to every numeral, this is what the test set looks like. I just need to remind you, the autoencoder has no idea of what a number is or a label to it. It only sees pixels. And even then, it's able to see the different representations of the pixel and the differences between pixels for different numbers. So this is really powerful in the sense that this is completely unbiased to a particular label, and we really enjoy and like this thing about the autoencoder. So when you get to the part of completing the code, you should be able to see something like this, depending on how well or how many neurons you assign to your autoencoder. If you chose fewer neurons, it may be a poorer representation than this. Now here's a question, trying to make you think or reflect on things. What can go wrong in this? What could happen with an outlier in autoencoders? One of the things that I like about an autoencoder is that outliers are usually treated equally as other data points, unless you purposely remove them prior to showing them to an autoencoder. And so in reflecting on this, what makes you an outlier? If we're looking at ourselves as individuals right now in Tapia, when you look around in the chat, or if you look around in the conference, what makes you different than the rest of the people here? When you reflect on that, what could possibly go wrong if we remove the outliers in a model? What are we taking away from the model, or what are we causing the model to have? So with this, I want you to realize the consequences of removing things that you don't necessarily like in data, and that unsupervised learning also has as a risk of trying to ignore outliers if you're not careful. Usually autoencoders would not do that automatically, but you gotta be careful and always look for those outliers and what happened to them in the input space and in the latent space. So at this point, I would like to take and answer a few questions before we move forward to our next module.